Okay, it was suggested that we give a logic example. I want to give an example from model theory. Take the theory of fields. I think I have correctly written the axioms. You've got an additive abelian group. You've got an additive group that's oh, that's not 1, that's x. You've got an additive group, it's commutative, and it's got additive inverses. You've got a multiplicative group of non-zero things, which is not required to be commutative. Wait, no, fields are required to be commutative. Skew fields aren't. Right. But for fields, we do require xy equals yx. Yes. And non-zero elements have multiplicative inverses. So this is an important theory, and people study a lot. They study models of it. In a model M of this or any other theory, but I'm just for concreteness, I'm talking about models of this theory. A definable set is a subset it's a settable. What shall I use for names of the things in there? A, B, C. Elements of, so n tuples of elements of the model. This could be triples of elements of the model or pairs of elements of the model, some n tuples, such that the model satisfies P of A, B, C, so on, for some formula P in the theory. So, for example, there's in fields, we can say x squared. I'm going to write x squared to abbreviate x times x, right? I didn't actually introduce a squaring function here, but you understand what that. We can talk about x squared plus y squared equals z squared. This is a formula of the theory. So we can define the set of all A, B, C in our model, triples of the model, such that the model satisfies A squared plus B squared equals C squared. We've got, it's certainly important, especially in the theory of fields, you study a model by talking about its definable sets. I'm afraid I'm going to need, well, we don't need these axioms. Early books on the subject talked about the category of definable sets. In fact, it was here in Beijing in 2007 at the International Congress of Logic, Methodology, and Philosophy of Science. Ehud Hrushevsky gave a talk. And he's a very important model theorist. He gets up and he says, I've been asked to talk about Kurt Gödel's influence in model theory. He said, this is a little bit difficult. Kurt Gödel was the theme of that conference. And he said, it's difficult because Gödel didn't work much in model theory. He said, so I'm going to tell you what we do. In model theory, we associate various invariant, we associate certain algebraic invariants to a model. For example, and he actually looked down and moved his hand in front of his mouth, said the category of definable sets in the model. He actually drops his head to say category of. He's too honest not to say it, but he knows that a lot of people don't want to hear it. So, a definable function in the model M. So we're not just dealing with abstract theory of fields, we're dealing with a specific model, a definable function in M. I'll just say it's a functional relation expressed by a formula in the theory. So, for example, there is a certain function from this theory, from this, let's take in the model R, take the standard real numbers as a model of field theory. There's a definable function okay, I was going to help you along. Okay, I will mention this. In the model R, the set of all x element of R such that the absolute value of x is less than or equal to 1 is definable. Because, okay, let's see, and so x less than 1, yeah. By the formula, there exists a y such that 1 plus x equals y squared. Among the real numbers, the numbers with absolute value less than or equal to 1, are just the numbers where 1 plus x has a square root. This is not definable in the model of complex numbers. Because in the model of complex numbers, everything has a square root. But in the model of real numbers, this is a definable set, because only positive numbers have square roots. So this is a definable set in this model, whereas if we look for all the complex numbers whose absolute value is less than 1, that's not definable in the model of complex numbers. For those of you who do model theory of fields, the point is R is an ordered field. In R, we can define the order relation. In R, we can define x is greater than 0 by there exists a y squared equals x. That's true of real numbers. But nothing like it is true for complex numbers. Every complex number has a square root. There's no restriction on a complex number at all to have a square root. In this, there's a definable function from the set of x in R such that absolute value of x is less than or equal to 1. To the set of x, y, z such that x squared plus y squared equals z squared. Set of x, y, that's not what I want. the set of xy such that x squared plus y squared is less than or equal to 1. In real algebra, we can define a function. Let's see, is that a definable function? Yes, it is. Yes. We can define a function that takes us from the closed unit interval and lifts it onto the top half of the circle. There's a definable function that lifts this up. Because it's defined by a formula here, we take the ones where y is positive, y has a square root, and this equation is satisfied. So in a given model, we can define some subsets, which may be very revealing about the model. We can define some functions. Every book on model theory now that talks about this subject at all explains that the identity function on a definable set is always definable. Well, sure it is. The identity function on any set is defined by the formula x equals x. That's the identity relation. The composite of two definable functions is definable, well, basically by taking the conjunction of the two definitions, existentially quantified. Yeah. So in every model, there's the category of definable sets and definable functions. Some books on model theory say it's a category, others just say there's definable sets and definable functions. Identity functions are always definable, and the composite of any two definable functions is definable. They feel they're making the subject easier by not saying, so it forms a category. I think they'd make the subject easier if they would say, so it forms a category. So I hope this is reasonably clear to people. You've got, even if you're not a model theorist, you've got a theory, you've got models of it. The theory says things about the things in that model. Some of the things you can define, some you can't. Okay, and so maybe I think for people who aren't model theorists, I should explain why you can't do this in the model of complex numbers. In the model C, set, well, yeah, for example, there's a set of all x, element of C, such that x is real. There is certainly a subset of that model of the real numbers, but it's not definable by a formula in the theory. There's no formula that you can define in complex algebra that says a number is real. There just isn't any such formula. This is a good subset, but it's not definable in the model. Let's see, what would be a function in the reals? Oh! Well, in the model R, the set of all x elements of R, such that x is rational, is not definable. You can't define the rational numbers by a formula in field theory. You can in arithmetic. Worse. The set x element of R. Well, worse or better, such that x is an integer. The set of integers is not definable here. There's no formula in algebra that picks out just the integral real numbers. And that turns out to be very important. The definable subsets of R, that is, the set of all x in R such that some formula holds of x. So now we're talking about one variable. Is the set of finite unions. The only things you can define here are finite unions of, finite unions of intervals, where I mentioned an interval can either be the interval from some a to b, the open set interval from a to b, where a is actually less than b, or a singleton counts as a degenerate interval, or we allow infinite bounds, or a to positive infinity. So intervals include intervals that go to infinity. Intervals include single points. All the definable sets are finite unions of intervals in this sense. That's all you can define in that model. This puts very strong constraints on what you can do in this model, and it turns out to put very strong constraints on the definable subsets of Rn, which I am not going to describe. Able to describe them. The definable subsets of Rn are pretty nice. So that actually people do sometimes prove hard theorems in geometry by showing that the theorem can be interpreted in definable sets in this model. And the definable sets of this model have such nice properties that if the theorem can be interpreted that way, it sort of has to be true. Lots of theorems in geometry that are not true for all topological spaces are true for all the ones definable in this model because they're very special. So given any model, now we've got the category of definable sets. And I don't know a standard notation for the category of definable sets.
The definable functions.
With the category whose objects are definable sets and arrows are definable functions. Yeah. I'll write def mod. I do not know if there's a standard notation for this. And if there may be a perfectly standard model. Def mod of M, the category whose objects are the definable sets, and arrows are the definable objects. Now this is a paradigmatic category of structured sets and structure-preserving functions. Definable functions, yeah, not objects, definable functions. Let me first make a typically category theoretic point. The theory also has a category of formulas which we think of as defining sets, but we don't look in a particular model. And formulas which we think of as defining functional relations between those, but we don't look in a particular model. Now that is not necessarily a category of structured sets and structure-preserving functions. There we just take any formula as defining a set, any functional relation, any relation such that for every value of this there's a unique value of that, we take as an arrow. But we don't do it in a particular model, then there may be no one model that captures that thing. There may be no. But for any model, we have this thing, definable sets and definable functions. And what I would like you to do, think of K as a field, and think of this as algebraic geometry over K. These are all the algebraic spaces defined by equations in K. If this was the reals, this is real algebraic geometry. This is all the algebraic spaces defined by real polynomials. If this is the complex numbers, it's all the algebraic spaces defined by complex polynomials. And maps have to be defined by polynomial relations. The maps have to be what are called regular maps, the traditional maps of algebraic geometry. So over R, this is just coordinate geometry like you learned in high school, except that we're allowing any number of variables in every degree of equation, which you just didn't do in high school. And now, if I have a map from K to another field, which can happen. This could be the rationals and map it into and include them into any algebraic number field. This could be the reals and include them into the complex numbers. This could be the complex numbers and include them into the field of rational functions on the complex numbers. There are lots of maps between fields. That induces a functor from the definable sets here to the definable sets here. That induces a functor from the category of algebraic varieties here. Okay, when I say algebraic variety, I'm allowing singular ones because lots of formulas define singular spaces. But this defines a functor from this category over here. Because if something was definable by a formula here, and then we substitute those things, this is a field morphism. So it takes polynomials here to polynomials there. It takes roots of a given polynomial here to roots of the corresponding polynomial there. So this will give, if this was the identity function, if this was just a field, we left it alone, well, we just left this alone. It would induce the identity functor up here. So there's a functor. So there's a functor from these to those. And this could be any theory. It doesn't have to be a theory of fields. Definable sets here and definable functions. Definable sets here and definable functions. When you change the base, you change all the definable sets and functions. Coherently, it gives a category. It gives a functor between categories. I will mention that more than that, we have a functor from the category of fields to the category of categories. Because if this was the identity, that's going to be the identity functor. And if we continue this on to some other field, redefining the points along this field map and then along this field map is the same as just redefining them along the composite field map. We actually have a functor from fields to categories. And in fact, this is for models of any theory. If we take the category of models of the theory and elementary embeddings, an elementary embedding induces a functor from the definable sets here to the definable sets there. It reinterprets these elements as being those elements. They don't satisfy the same formulas. The formulas have been changed, but they satisfy the corresponding formulas. Your elementary embedding has changed the meaning of some of the parameters in the formulas. Good enough. They satisfy. So for any models of any theory, elementary embeddings give functors between the categories of definable sets. And in fact, the category of elementary embeddings now gets a functor to the category of categories. Assigned to each model, it's definable sets. But assigned to each embedding of models, the corresponding functor of definable sets. If this embedding was the identity, that's not going to change anything. Embedding here and then there is certainly the same as just embedding here directly to there. So we've got category theory appearing on a couple of levels. There's a category of definable sets for each model. There's also a category of these categories. there's a category of the models. Yeah.
Excuse me, so I think maybe your model must be the first order.
Oh, yeah, I'm talking first order theories here. Yes,
Okay.
yes, absolutely. Absolutely. I know nothing about models of, no, I don't even, yeah. I'm talking first order theories here, yes. Yes. And that's the power of this method. Because the theory is first order, but the description of a given model need not be first order. We know lots of things about the real numbers and the complex numbers that is not first order in the theory of fields. So we take what we know about all of them and we compare it. This is only what's expressible in the theory, not everything we know. And so by stripping down everything we know to just what's expressible, we get a powerful tool. You know. Okay. I don't have more to say about that offhand, but I hope that helps. They say this is already a category. Because we have the definable relations. Well, I could talk more about algebraic geometry, but I don't know if it would help. Natural transformations. Here. Well, I don't know. I haven't thought about natural transformations in that context. Anyway, in both category theory and general mathematical practice, what's important about functors is actually how they relate to each other by natural transformations. As we get to higher powered equipment, it's a little harder to see. I've mentioned before, Eilenberg and McLean discovered natural transformations first. They defined functors so as to explain what natural transformations are. And then they defined categories last to explain what functors are. No, this doesn't, don't read this. It's okay, it's true, but it's not helpful at this point. Here's what a natural transformation looks like. Okay, that picture is maybe not helpful right at first. A natural transformation goes from one functor to another. Here we've got the network of arrows of A. Functor F is turning that into something in the network of arrows of B. So we may have mashed a lot of things together, but we haven't torn anything apart. We may have made things equal that weren't, but composites still are still composites. Maybe some other things have become composites that weren't, but everything that was still is. G has mapped it also over here, maybe to a different place. So for example, an example that some people, so this might be the category of sets, and this could be the category of topological spaces. Now there's a functor. From sets to topological spaces, you take every set to the discrete space on that set. It's a topological space where the points are all separate. Every subset is an open set. There's another functor from the category of sets to top, where you take every set to the indiscrete topology on that set. The points are the elements of that set. Only the whole set and the empty set are open. So no points are separate. The discrete functor separates all the points. This set becomes a topological space that looks like dust. The indiscrete set, this functor glues them all together. It takes every set to the topological space that just looks like a ball stuck together. A natural transformation flows this picture down to that one. And indeed, you can take every discrete topological space, there's a continuous function from it to the indiscrete one. If these points were all dust, there's a continuous function that glues them all together. It didn't tear anything apart. There was nothing to tear apart, there was dust. There's a natural transformation. Take the discrete topological space to the indiscrete space on that same set. There's no natural transformation from the indiscrete up to the discrete. No, there's not. Certainly, just taking each point to itself is not a continuous function, because in the indiscrete space, the points are all glued together. In the discrete space, they're all separate. A continuous function can't take them and separate them apart. There is a natural transformation from discrete to indiscrete, not one the other way around. What I want you to think of now, what I'm hoping you'll think of, just thinking of categories in general as a network of maps. A functor is a depiction of one network in another. And a natural transformation takes one depiction and flows it down to the other. I have not defined precisely what that means. And the idea is not to define precisely what it means. I want to illustrate by examples, which we'll end up defining. But a natural transformation is natural in two ways. Technically, certain composites are equal to each other. That's how everything works in category theory. Some composite is equal to some other arrow or some other composite. Intuitively, every arrow does the same thing to f of a as any other does to its everything. So, intuitively, whatever this did here, we took the discrete set of points and glued them all together. We also took this discrete set and glued them all together. We took this discrete set and glued them all together. We did the same thing everywhere. That's one of the motivations for calling them natural. Another is that certain squares, which I've drawn here, commute. Okay, but I'll get to that. Well, we can see this with the fundamental group functor and the first cohomology functor. Of course, I can't explain that in a lot of detail, so more simply and logically with product functors transforming to identity functors, and I'm going to do that one first. See, I already decided this morning. I'll do the simpler one first, even though, like I say, it has the disadvantage that it just looks like category theory feeding on category theory. But it's easier to see. It seems as if taking a set's product with B and projecting it, I'll write it this way, and projecting it onto A. This seems like a natural thing to do. Let's, in terms of our set theoretic intuitions, this was the pair AB, and we're going to assign it the element A. It seems like this is a natural thing to do, and we can do it the same for any product with B. This ought to be a natural transformation. Can I make a slide for this? Oh, yeah, I just gave the, I just gave that. The definition of, so on the one hand, what do we know, given A and any function from A to A prime, we know that there's a function f prime cross f cross B P1, P prime line. What we know about this function is that it makes this square commute. And this is what we mean by naturality. So, I've got A and A prime, and there's this arrow here, and I've got various other arrows, and this is one copy of the category A. This is some other arrow. There's lots of arrows over here. And I've got two functors from this, again to A. In this case, remember the product functor took objects of this category to other objects of the same category. I've got one functor where I took everything to A cross B. So one functor floated over there. I've got another natural functor that just leaves everything alone, the identity functor. Now that's obviously a functor. It takes every object to an object. It takes every arrow to an arrow. It takes identity arrows to identity arrows because it didn't change anything at all. It takes composites to composites because it didn't change anything at all. That's a functor. A natural transformation from one to the other is a set of arrows that flows it, and I'm telling you that that's just the projection functor. The projection functor is natural. Think of all these. These are all A cross B, A prime cross B, A three primes cross B, A double prime cross B. These are all now just A prime, A three primes, A double prime. And these are now all the projections. This commutes. This is part of the definition of that arrow. Well, what was the definition of that arrow? The definition of that arrow was just that all the composites here are equal. All the composites that could be equal are equal. We defined that arrow as being the thing that made that composite equal that one, and that composite equal that one. So certainly, this composite equals that one. That's the naturality square. So intuitively, first projections did the same thing to every object. And further, first projections commute with any arrow. It doesn't matter whether I go over by the product functor and then project. I take A by the product functor and then project, and then I look at the identity function on that. Or I take the arrow over by the product function and then project and take that composite. I get the same thing. That's actually just my definition of the functor. So this function, the functor blank cross B from what I'm here calling the category boldface A to itself. I'll try to write bold A. Is defined by saying first projection is natural from that function to the identity. Part of the definition of this functor is just that projection is a natural transformation from it to the identity. Projection sort of undoes that functor. It takes it back to it takes it to the identity functor. Right. I didn't put the projection functor onto this. Oh yeah, here it is. Yeah. The definition of this arrow was that projection is a natural transformation from it to the identity. I'm trying to think about natural transformations in the category in the model theoretic context that I just gave.
You cannot say. The definition you just erased
Yeah.
used the functor itself. So, and
Yeah.
you define the functor by saying if it's a natural transformation, but actually you just used the natural transformation for this particular object, not the whole thing, right? Otherwise you will have a circularity.
Yeah.
You just say for this
yeah.
particular A cross D thing, you have the property of natural transformation. Is that?
I was using define loosely there. I'm not sure that I couldn't use it strongly, but I didn't have that in my mind. I was using it just in the sense that the definition of this functor.
Yeah.
Oh, right. The definition of this functor, well, it says something more. So it also says, this definition also says that the second projection is a natural transformation from this functor to the constant functor B that assigns everything the identity arrow on B. And that actually is a unique definition. No, still not. It's still not. But it's still. So as of now, I believe I have to define the functor the way I did here. But I can now summarize this definition by saying, this definition tells you projection onto A should be a natural transformation and to the identity functor, and projection onto B is a natural transformation to the constant functor B. But probably, as far as I can see now, still officially I have to give you this definition. I can't just use those. So another part of that so now we've got another thing. Let this be the product functor, product with B again, so this is now the same category as that one. Product with an object B, and this takes everything to B and the identity function. So this is all contracted down to a point down here. This is just B, and it's all identity function. But projection onto B still is natural. It still makes all those squares commute. The definition of natural is that all these squares commute.
Maybe it's good to write down the definition.
Yeah. For any functors, F and G, both going from a category A to a category B, a natural transformation tau from F to G, and sometimes people put a point there to indicate it's natural, but I'm just calling it a natural transformation, is an assignment of an arrow in B, tau little a goes from F of A little a to G of little a for each object A in my category bold-faced A. So for this object, I assign that arrow. For this object, I assign that arrow. For this object, I assign that arrow. Such that for each arrow F from A to A prime in A, we have A down by F to A prime. We have F of A. Wait, do I want to draw that direction? No. No, here I want to draw it this direction. We have A going over to A prime. So we have F of A So that's f. F of f goes from f of a to f of a prime. G of little f goes from g of a to g of a prime, tau a prime, so that this commutes. That composite equals that composite. The definition is simply, for each object, we assign an arrow of this category, such that for any arrow here, the square formed by f of that arrow and these two assigned ones and g of that arrow commutes. The composites around both sides are the same. And maybe at this point, you're looking at that and see, okay, it's pretty, it's symmetrical. You can see how it fits together grammatically, but what's the point of it? Well, I'll rather erase that. For each arrow F over here, we had A cross B by F cross B to A prime cross B. And we had A going over by F to A prime. The natural transformation assigns first projection. That's what's going on. It's natural means it doesn't matter whether I look at this functor's value for f and then transform it away, look at the function's value for f and then transform it away, or whether I transform the functor away and then look at the arrow. Transform the functor away and then look at the arrow. I get the same thing both times, and I hope now this square makes a little more sense to you. You see what's going on with that. It's saying it doesn't matter whether I start with the product, do the math within the product and then project, or whether I start with the product and project and then just do the math. And this is not only true of the product functor. I guess the point I'm clear I want to make, it's not just true of the product functor that this is natural, it was half of the definition of the product functor that each of these squares should commute. So, Riemann sort of knew, and Poincaré knew very well, there's two ways I could look at this. I could look at paths on that space, and we've talked about that. Or I could look at these as cuts, cutting the space into parts. And I could ask which cuts really do cut it into parts. On a circle, every cut cuts it in two parts. There's a part inside and a part outside. And on a sphere, rather. This is a sphere surface. On a sphere surface, any curve I put cuts that into two parts. On a toral surface, on a torus, some cut it into two parts, but others don't. Others just cut it open without cutting it into two parts. Riemann said, are these the same thing? Can I keep track of paths? Is that the same thing as keeping track of which paths cut it into two parts? That would be great if deformability of paths was the same criterion as whether the path cuts it into two parts. But he found they're not. He found if we call two paths equivalent when the two of them together cut this into two parts, we get a different notion of group than if we call them equivalent when you can deform them. This is a coarser notion. This group is not associative. In particular, doing path A and following with path B is not equivalent to doing path B and then following with path A. But let's mash this group down by just declaring them equivalent. Let's just say any path like this, we're going to set that equal to 1. We're just going to call that path trivial. It's not trivial in the fundamental group. This path is, in general, not deformable to a point. but let's call it trivial in our calculations. Let's get a simpler group by calling some of the elements in our original group trivial. That'll simplify things a lot. That simplification leads from the fundamental group to what's called the first cohomology group. Also an important one. Cohomology, Poincare already knew to calculate the first cohomology group of any manifold, take its fundamental group, and make it commutative. We just insist not only paths that can be deformed into each other will be identical, but paths that could be deformed if we change the order of composition will also be called identical. That turns out to be the same as calling two paths identical if together they cut out a piece of the manifold. Now obviously, if two paths, let me give a little more of the plausibility of that. This path can be deformed into that path, or we can deform it into that path. We'll just push it over here and stretch it a little bit. And these two cut out a piece. Right? Anytime one path can be deformed into another, it should be plausible, the two paths will cut out a piece, namely the part that was covered by the deformation. So paths that are equivalent in this sense are certainly equivalent in that they cut out a piece of the manifold, but not vice versa. Actually, on the torus, they are equivalent, just in case. On the single torus, if they can be deformed, if they cut out a piece, they can be deformed into each other. But that is no longer true on the two-hole torus. Here, some that cut out a piece can't be deformed into each other. So we're going to call, but it's still the case that if they can be deformed, they do cut out a piece. So if I take the fundamental group defined by which paths can be deformed into what, I can identify some things with one and get the cohomology group. I can take that group and I can just kill some of its members and get the other group. That is a natural transformation the fundamental group functor, remember this is a functor from topological spaces to groups. The first homology functor, I've been saying cohomology, but Poincare did it for homology, and it's not, is also a functor like this. Now some of you will know it in fact is a functor to abelian groups. Homology groups are always commutative. But the point for us is that taking this group and making it commutative is a natural transformation from that functor to that one. I can work with fundamental groups and then make the groups commutative, or I can make them commutative and then work with the commutative groups. It'll come to the same thing. And this is how Poincare normally would calculate the first homology of a topological space. That's it. And yes, I thought, yeah, so we really, there's time to go more into that one. So tomorrow we get more to logic. Tomorrow I'll introduce the elementary theory of the category of sets, the category of categories as foundations. We'll do some more specific instructions, probably not in a lot of detail, but I'll get into two extensive categories, examples, category of sets and category of categories.
他跑过来就是有这样的是吧？刚刚好了。
Questions, thoughts?
他尽量就是这样的。
对，他就是一次换一次。
啊，A 上面写是 A 页是什么 ？A4 页，A 页是什么？出来 A 页了。我是这么做的，我做过它。这是被群的，它就可以往上写的东西，它是个得有的。
Okay, what I'm talking about now is sort of elementary algebraic geometry.
哎，是 object。
What's definable?
它刚才是不是在说群呢？应该是在说群的。这个 A 是一个什么？
In the theory of a field.
我不知道。它刚才
And
是什么
in a model M.
这个它有个就把它要注解。
Is solutions to x cubed times y squared minus y squared x equals 0. That's what we can define is solutions to polynomials.
群是
But not only that, it's also things like for some y. So we can also quantify. But basically that's what we've got. We've got quantification and solutions to equations. So the definable sets are the sets that you can get by definitions like this. Now, in some sense, these are the sets of algebraic geometry. They're not exactly algebraic geometry because in classical algebraic geometry, for example, well, we don't allow singularities. We can define, you can define a curve with a cusp. What is this? This is, am I going to get the x and the y wrong here? X cubed minus y squared equals 0. The solution stat either look like this or rotated 90 degrees. I forget which is x and which is y. In classical algebraic geometry, we don't like this because it's got a singularity here. In definable sets over a field, we like it fine because this is a perfectly good equation. So the only difference here is that definable in a model over a field is like definable in classical algebraic geometry over that field, except that we also allow bad behaviors that the classical geometry didn't. And we allow quantification, which classical algebraic geometry doesn't. So it's sort of quantified algebraic geometry. So it's very interesting. It's certainly, it's an important fact about the reals that there's an algebraic definition of positive reals. A real is positive if it has a square root, if it's equal to the square of something. There's no algebraic definition in the complex model of the real numbers. There's no equation in complex algebra that only real numbers satisfy. Or no formula even, not just equation, no formula. There is a formula in the real model that only the positive numbers satisfy, namely for some y squared equals x. So it's a little more general than classical algebraic geometry, but yeah, definability in a model is a lot like algebraic geometry over that model. Certainly algebraic geometry is included in this.
With Colin briefly during the break, maybe Colin can point out the concrete proof of some basic things you mentioned.
Oh yeah.
Right.
Yeah, I was gonna
give some reference.
Oh, yeah.
So you can check the concrete proof.
Yeah.
I think that will help because it can be a little bit too fast.
Yeah. Well, I'll pass on the name of a book you mentioned that I haven't read. Bob Kuka, who's a smart guy. I think he's a little bit crazy, but he's a smart guy. And that was called Category Theory for Kindergarten? Yeah. I don't know if he gives proofs. Steve Audi category theory. The references of Steve Audi category theory will prove all these things pretty early on. And I can't help but mention my own book. You can leaf through it. And the proofs there are a lot like the proofs I give here, elementary categories, elementary toposes. These toposes, these will give proofs of all the things I've read. And you look at the index and just go straight to that proof. They may not occur in the first chapter, but they'll occur in the first paragraph of some chapter, and so you can look at them. If you want to understand this material, I have to mention two books by William LaVere. Sets for Mathematicians. These books will not give proofs of those results. These books are more conceptual. They're attempting to give overviews. They won't help with these results, but they're worth looking at, and Conceptual Mathematics. These are good introductions to how LaVere thinks of the subject, but they won't give proofs. I don't know if this book gives proofs. These books certainly give proofs. So there's that. Also, any of these things that I don't prove in so much detail, if you want to prove, you can ask and I can do it. But I will say tomorrow is going to be more about details. Tomorrow we're going to look at particular theories in more detail. So.
See you tomorrow.